Today, we're going to pull back the curtain on the invisible magic that lets your computer do a million things at once without breaking a sweat. We're talking about memory management. I mean, have you ever really stopped to think about it? How in the world your computer handles a dozen browser tabs, a video playing, and your music streaming all at the same time without just completely giving up? Well, that's the exact puzzle we're going to piece together today. All right, to really get this, let's imagine the main character in this whole story, your computer's processor, the CPU. This thing is an absolute speed demon. I mean, it can blast through millions of instructions every single second. But it's got one little quirk. It hates waiting around. It just wants to go, go, go. So here's where the drama starts. You've got this lightning-fast CPU, but other parts of your computer, well, they're not so fast. Take the hard disk, for example. It's way, way slower. So what happens when a program needs to grab a file, like opening a photo or loading the next level in a game? The CPU has to hit the brakes and just wait. And for a speed demon like that, this is torture. It's a huge waste of power.
So how do we solve this problem? How do we keep our speedy CPU from getting bored? Well, that brings us to the whole art of multitasking. Let's dig into how operating systems pull this off.
The secret weapon here is something called the degree of multiprogramming. And honestly, it's a pretty simple concept at its core. The idea is to cram as many programs as you can into the computer's fast memory, the RAM. That way, you've always got a lineup of jobs ready and waiting for the CPU to tackle. And the difference this makes? It's huge. If you've only got one or two things in that memory queue, that's low multiprogramming. The CPU is going to end up waiting a lot. But with a high degree of multiprogramming, the second one task has to wait for that slow hard drive, the CPU just instantly pivots to the next job in line. This keeps it busy, and it's what makes your computer feel so snappy and responsive. So, if you take one thing away from this, it's this. The whole game of modern memory management is to keep the CPU's to-do list packed. So packed that it never runs out of work. One task hits a roadblock, no problem. There's always another one ready to go, keeping that processor humming and your computer running like a dream. Okay, so how do they actually do this? Well, engineers came up with two main strategies over the years. Let's check out the first one, which is called contiguous allocation.
The idea behind this first method is actually really simple. When a program needs to run, the operating system looks for one single continuous empty block of memory that's big enough for the entire thing, and it just slots it right in there, all in one piece. You can think of it like a really strict librarian who insists that every single book by one author has to sit right next to each other on the shelf, no exceptions.
And you can see what that looks like. The process just sits there in memory, all nice and neat, taking up one solid block of addresses. For the operating system, this is super easy to keep track of. It's clean, it's simple.
And this isn't just some abstract idea. This is how they did it back in the day, back in the 1960s, with those giant room-sized mainframe computers. It was the first logical approach, but it had a really big problem. It was super wasteful. What if you had lots of little empty spaces, but none of them were big enough for the new program you wanted to run? All that space just goes to waste.
And that exact problem, that inflexibility, led to a much smarter, much more modern approach. Let's talk about strategy number 2, non-contiguous allocation. Okay, so this one flips the script completely. Instead of looking for one giant empty space, the operating system takes the program and chops it up into smaller, equal-sized pieces. Then, it takes these little pieces and just scatters them wherever there's an open spot in memory. Any little gap will do. The OS just keeps a detailed map, like a table of contents, so it always knows where every single piece is.
And this is the real genius of it. Now, a single program can be spread out all over the place, using up all those little leftover gaps in memory. It's like being an expert at packing a suitcase. You find a way to use every single nook and cranny, wasting absolutely no space. So let's put these two head-to-head. The first strategy, contiguous allocation, it's simple for sure, but it's also rigid and wastes a ton of space. The second one, non-contiguous, is definitely more work for the operating system to track, but it is incredibly flexible and super efficient. And that efficiency, that's exactly why it's the standard for pretty much every modern computer you can think of. Okay, this all brings us to the big so what? Why should you care about any of this? Well, it's because this clever strategy is, and I'm not exaggerating, the foundation of your entire digital life. Yeah, this isn't just some dusty theory from a textbook. This whole idea of breaking up programs and scattering the pieces around, that is the magic trick that makes smooth multitasking possible on your phone, on your laptop, on pretty much everything you use every day.
I mean, just think about it for a second. When you instantly switch between two apps, that's this at work. When your computer is downloading updates in the background while you're still working, that's this too. That feeling of having like 50 browser tabs open and your computer doesn't grind to a halt, you can thank non-contiguous allocation for that. It's all about squeezing every last drop of performance out of your device by being super smart with memory.
So we've gone from these simple, clunky blocks of memory in the 60s to this incredibly clever, flexible system we use today. Memory management is always evolving. And it kind of makes you wonder, right? As our apps and our games get even bigger and more demanding, what's going to be the next big memory puzzle we'll have to solve?